Hello, this is E637 and I'm Charles Bouman, and today we're going to pick up with color again, talking about chromaticity diagrams and that material. So today is going to be an electronic day. We're going to use the computer to do this. So let me bring up the notes. Oh, what happened with Liz Taylor? I hope nothing bad. I'll never be matched. Oh, okay. No, nothing bad. Okay. Let's see what we got. Course information. Yes. Okay. So.
We have extra notes from.
Oh, okay. Oh, thank you. Thank you. So, visual supplementary. Okay. Yeah. I'm sorry. Color spaces transform. Oh, hold on. And we need to do stimulus models. Okay. Okay, here we go. Okay, so here's the chromaticity diagram. Oops. There's the chromaticity diagram. Can we switch over to the computer? Oh, yeah, good. There's the chromaticity diagram we showed last time. And let's see. I need to zoom out a little bit. Okay, there we go. So, and we saw that. Okay, so the this space here going from 0 to 1. Here it ends at 0.8, but we could conceptually extend it to 1. Okay, and from 0 to 1 here. Okay, and then the relevant part is the part that falls inside of a triangle. And this is the space of colors, okay? This is a sort of a generalized concept of color that's spanned by the values of x, y, z, where x, a little x, y, z, or little x, y equivalently, where little x, y, the chromaticity values are strictly positive. And of course, the chromaticity values need to be strictly positive, so it's the only relevant range, okay? But this range includes things that are not real colors. They're what's sometimes called imaginary colors, because, for instance, the value 1 here, 1, 0, 0, 1, okay? That would be the little y is 1 and the little x is 0. That corresponds to the theoretical imaginary primary associated with the y component of x, y, z, but it's not a real color. By saying it's not a real color, I mean there's no physical spectrum of light which will produce that response in a human with normal vision with that input. I once knew a person who's had, I think, damaged his what is it called? The lens in his eye, okay, or something. It was something in his eye, okay, and so they had to surgically replace it with. I mean, his vision was basically fine. I mean, he was okay, so you don't have to feel bad, okay. But if you look really close, you notice that the pupil in one of his eyes looked funny. It looked a little different. You didn't really notice it, but he had damaged the lens in that eye so that it's the properties of I guess your lens is, even on the normal vision, has some absorption of light. So the spectral response of that eye was different. So he was sort of like Superman. He could see ultraviolet light or something like that, you know. Or infrared or something. I don't know. Maybe it wasn't even true, but I believed it, okay? So So he had like superhuman vision, okay? So we would have to exclude that person from this experiment, okay? Okay. We don't want to measure any people with superhuman vision. But for normal people, there is no input stimulus that will produce this output, okay? Okay, and then this over here would be the primary associated with X, and over here would be the primary associated with Z, right? And, okay, now, if you take pure spectral, if you take pure monochromatic spectra, okay, so they only have a single wavelength of light in them, between 400 and 800 nanometers, outside that range of 400 to 800 nanometers, you either can't see it or it might, like, you know, irradiate you. Like X-rays or something like that, but we'll ignore that. That's too far out, okay? It would be like infrared or ultraviolet, right? So you don't have to worry about it. So those are all the pure spectral colors, okay? And you can plot what their chromaticity is. By the way, chromaticity does not uniquely specify color because there's also lightness, okay? Or brightness, depending upon your perspective. But the chromaticity, as you move along this curve, changes at different wavelengths. So that curve forms a surface. By the way, you can see that even at 10 nanometer steps, there's some pretty substantial sampling artifacts, right? I mean, this curve should be smooth, and it's not, right? So now, can you see that visually? Well, actually, the honest answer is I don't really know, but it's not obvious you can, because perturbations in this chromaticity space are not necessarily proportional to your sensitivity visually. So in some parts of the space, you may be very sensitive to small errors, and here you may be very insensitive. In fact, that is the case. How insensitive, I'm not exactly sure. So I don't know if you could see that or not. You probably could if it was under super ideal situations, because in fact the standard for CIE actually includes specifications on how to do the interpolation, which we haven't gone into that. But here I'm just doing linear interpolation. But you can see that, so you can see that it's kind of interesting. Even though 10 nanometer steps seem pretty fine, it's not necessarily fine enough to represent precisely the human visual response. But in any case, this is the curve that, approximately associated with the chromaticities that you get from the spectral, as a function of a spectral wavelength. And that curve, this curve, is not a property of the physical world, okay? Well, okay, it depends on how you define the physical world. It's not a property of the physics of light. It's not a property of, it's not a result of Maxwell's equations. It's not a result of the theory of relativity or quantum mechanics. It's how humans behave, okay? So this is not like something like pi. Pi is the ratio of the circumference to the diameter of a circle. That is, depending upon your philosophical beliefs, something that is kind of fundamental to the to like logic, right? And sort of transcends the physical world. Okay. But this is and it's not even just a property of the physical world, like Planck's constant. Planck's constant is the ratio between the energy of a photon and its frequency. Okay, so given the kind of modern theory of quantum mechanics to the degree that I understand it, one would believe that Planck's constant is a constant. The fact that you use the word constant suggests that it's invariant to things, right? That ratio is fixed, independent of things like, whether you got your homework done last night or the phase of the moon, okay? But maybe there's an effect there. Maybe if you don't complete your homework, Planck's constant changes slightly, okay? That would make it a less useful concept, okay? But this is a property of something even smushier than the physical world and logic. It's a property of humans. So you have to just measure it, the structure here is purely mathematical. So that's, not something you have to worry about measuring. You just derive the equation and it's true. But this curve you have to measure. That's a physical measured property. So, and it could vary a little bit from person to person, but the assumption is it's approximately constant. Now, the three dots here, so there's two triangles. The three vertices of the triangle, so there's two triangles. The one triangle is the CIE, it's a triangle associated with the CIE primaries. The CIE primaries are pure spectral primaries, so therefore they fall right on this curve. Exactly, because they're pure spectral primaries, so they're by definition on the curve. And that triangle there is the set of chromaticities that would be produced by the linear combinations of those three primaries. That triangle is not a property of the human beings. That's a property of the physical. That's a result of the physical properties of the primaries, wavelengths, and the mathematical structure and definitions we have for what chromaticity is. And then by combining together those three primaries, we can get all the colors in this region here. Okay. Now those primaries are not very practical because they're pure spectral primaries. So you would need to have a display device which had the ability to produce pure spectral components. And there would be other side effects which would be problematic. Like for a printer, it simply wouldn't be possible. You'd have to have a fluorescent dye that re-emitted at that wavelength. Because otherwise, if you made a printer that was with an ink that only reflected light in a very small wavelength, guess what the ink would look like? So if I had an ink, okay, which only let through 10 nanometer light within a 10 nanometer band right there, okay, and I put that ink on a piece of paper, do you know what the paper would look like?
Dark?
Black, yeah, pretty much black, right? Because most of the light would have been absorbed. Only a small amount of the light would be reflected. The fact that its wavelength happened to be at that particular wavelength is almost irrelevant. If this is green, okay, so it'll be a very slightly greenish black. All right? So with printed material, you have kind of an additional constraint, which is since you can only absorb light and you can't emit it, you'd have a problem. Now, on an emissive display, you could have a source of light that was just pure spectral green, but that would be expensive to produce. So there's problems. So instead, they back off and they say, well, okay, we'll have a green which is a more achievable, practical green that would be the result of a broader spectrum of light, and a blue and a red. And they've decided on this, and it's been standardized, this so-called 709 primaries, which are widely used in commercial imaging devices. There might be some future time in which they try to expand this gamut. There have been different standards for the color primaries through the years in even commercial imaging applications. Some of the earlier primaries were less saturated, so they had a narrower gamut, but they were more practical to achieve. But if you go by TV at Best Buy, it's going to have, or in any other store, it doesn't actually have to be Best Buy. It'll have effectively these primaries, these 709 primaries. Either the phosphors or not phosphors today because now they're LCD displays. Either the LCD display will be designed so it physically produces these colors, or it'll produce colors relatively close, and then the software inside of the display inside of the TV will do some kind of colorimetric adjustment so that it appears that the inputs are producing exactly those colors. Okay. And then white is in the center, and equal energy white is here. You can see that's equal energy white, and that's D65 white. D65 white and equal energy white look quite different. I mean, it's not a subtle. well, it depends on how you define subtle difference. But I think any normal person with normal human vision will look at the equal energy white and D65 white, and they would obviously be slightly different shades of white, okay? And so here, a small difference is pretty visible. D65 is yellower, I believe. Is that correct?
Bluer.
Blue. It's bluer. Okay. I knew it had to be one of those two things. Actually, you can tell it's bluer because bluer is this direction. So this would be blue-yellow, and this is red-green. So it's got to be bluer. Oh yeah, that's right. It's bluer. So it's a cooler white than equal energy, I guess. Okay. So now, okay. So out here in this region, that color is imaginary. Because, and then let me just talk, this line here is called the extra spectral colors. So these colors are as saturated as you can get. See, the colors, saturation now has a more precise definition. The colors on the outside of this curve are referred to as more saturated because they look like purer colors. Now, they can be light or dark, but they're saturated in those cases, okay? So in the case of, like I gave the example that if you had just the lightness, each of these points in chromaticity specifies an infinite set of colors, right? So now, if you take red and green and you take linear combinations of those, they fall along this curve here, and those are saturated colors, but they're not pure spectrally. So not all what you might call pure colors are pure spectrally. These can be formed by a combination of red and blue. And in fact, I forget how this works exactly, but I'm pretty sure that experimentally, okay, one of the primary colors, I probably shouldn't say this because I'll end up getting it wrong, but I think to make the pure red, so in other words, this is viewed as violent, right? And either blue or red, in order to get what people perceive as a pure blue or a pure red, you actually have to add a little bit of, I think you have to add a little blue to the red to make it to this spectral color here. So the pure red is actually around here or something like that. At least what people perceive as pure red. So this extra spectral line is important, but it includes purple. So anything in here, anything inside of this convex curve, we can produce, that color can be produced through a combination of pure spectral wavelengths. And the way to produce each color is not unique, right? There's an infinite variety of ways to produce the same color. And different spectral combinations that produce the same color are known as metamers, okay? The same perception of color. Do you have a question? Oh, okay. And okay. And so out here, how do we refer to those colors?
Imaginary colors.
They're imaginary, right? And in here, these are all real colors, okay? Now, so then the question is, well, what does it mean to be either inside of this triangle or outside? Inside the triangle, it means that that's a color that we can produce through a combination of these three primaries. So if you have a display device that's emissive and it has three primaries that can be modulated in their intensity, then these would be the range of colors that could be produced by linear combinations of those three primaries. If you're outside the triangle, what does that mean? It means that those are real colors, but you just can't produce them with a combination of these three primaries. So if your device physically uses those three primaries, that means that those colors are out of the gamut of that device. So how would you increase the gamut of this device? Any thoughts?
Add a fourth primary?
You could add a fourth primary. You could put a primary out here, right? And then you can produce any color inside of this quadrilateral. So let me draw that on the paper here.
A physical property. It's not.
We can switch over to the paper maybe. So if we have 3 primaries, we might have like this. If we added a 4th primary, then we could produce any of these colors, right?
Mm-hmm.
Now, interesting thing is, now if we want to produce some particular color here, if I have 4 primaries, how do I go about doing it?
Some choices. Yeah, lots of choices.
Excuse me?
I was going to say you have lots of choices.
You have lots of choices.
Yeah.
In fact, exactly how many choices do you have?
Infinity.
Infinite. So you have an infinite number of choices, right? Because I can also draw a line like this, say, and then it's also in that triangle. So I can form it by a combination of these, or I can form it by a combination of these. And then what I could do is I could take any linear combination of those 2 results, and they all produce the same color. Are those colors? Those colors would have, what word describes them? It starts with an M.
Metamer.
They'd be metamers, right? Because they'd have different spectral distribution, but they'd produce the same perceived color match, right? Now, so in this case, the mapping of a desired color to a particular way of producing it on the display would be non-unique. So there's actually a test question on this, by the way, somewhere in the old exam problems. Okay, that this happens a lot in applications like printing, not so much in display, but in printing you might have at the very least, a very common situation is you have CMY. That's 3. So with 3, you could produce any specific color, but in addition you have K. So that's going to give you 4 colors, right? So in this case, the way to produce a particular color is not going to be unique, because there'll be a lot of combinations which could produce some colors. So, but then in addition, what happens is they might have like a saturated cyan and an unsaturated cyan. So a typical situation is that you might have, you could have 6 colors here, plus K would be a 7th color. So you could have like a 7-color printer. So what's the advantage of having 7 colors?
Perception.
There could be more than one advantage, but what are some obvious ones? Gamut. You'd have a wider gamut. So it might be that some of the colors in your printer can't capture the great beauty of your photographs, right? So you'd want to have greener greens and redder reds. Yeah?
But it is interesting that when we have a photo, for instance, it's JPEG and it has Rgb, and then we want to print it with, I don't know, 6 colors.
Yeah.
How does the printer do that? I mean,
so your concern is that the printer's gamut, how can the printer's gamut exceed the format's gamut, right? Yeah, exactly. So well, first of all, it turns out that, and so it's a big mess is the answer, okay? So the printer's gamut the conventional wisdom is that the printer's gamut is not as wide as the display's gamut, but that's not entirely true. In some places, printers tend to have narrower gamuts than displays, and this particular problem, which is that printers are restricted because the inks, unless they're fluorescents, they can't. They can only absorb light. They can't produce it. So that the display, the brighter colors particularly, tends to have a broader gamut, but the printers can have actually a broader gamut at the darker colors. So and both those things may have broader gamuts, but typically have less broad gamuts than the format. Okay, so it's kind of a big mess, and that's why if you buy a camera, if you buy an expensive camera, usually it'll have like and we're going to talk about this in a little more. It'll have a sort of a JPEG format. In the JPEG format, usually what it'll do is it'll use what we'll call what we're going to talk about is Srgb. But there are other RGB formats. For instance, there's an Adobe RGB format that's not as widely used. But in addition, a good camera will usually have a RAW format. Okay, RAW means that they just plop the sensor data down on the chip. Okay, so if you measure the sensor data, hopefully the sensor data is taken in a subspace of XYZ. All right, so if you haven't processed the chip if you haven't processed the data, you have as much information as possible. So the camera can, in principle, capture a wider gamut than could be stored in a JPEG format. And that's one of the major advantages of using RAW format. So if you're a professional photographer, you may capture the images in RAW format, or you may simultaneously capture them in RAW and JPEG so you can view them as JPEG and store them as RAW. And then later you can take the RAW and it's got all that good data in there that you can extract out all the finer colors. But particularly in dark areas, Srgb can lose subtleties of the color. And I like one of my favorite examples. I don't know if it still is the case. It probably should be. Okay, but it used to be like if you watch like the Winter Olympics, they would wear these really like bright fluorescent orange like ski suits, or I'm not a sports person, but it seems like in sports, they always try to push the boundaries of having more intense colors, okay? Probably because it increases consumer participation, okay? But anyway, so what would happen is that when you look at the picture of the person on the ski slope, they just look like flat, you know? Well, that's supposed to be their head. So they would look like a flat red, okay? Totally flat. Because, guess what? It's saturating the color format. It's not even just the TV. You're probably just pinning the one of the values that's clipped. So, so what'll happen is, now if you fall outside a gamut, so let's say this is the gamut of the device. This is a simple case. So it's an emissive display with 3 primary colors, right? Or it could be a format. We're going to talk about that some more later. That's an RGB format, and the format uses these values, and each value is stored as an unsigned character. That's 8 bits. So 8 bits goes from 0 to 255, as you well know, right? So you can only store those values for RGB, right? Now, if the color, it comes over, let's say the color is like a supersaturated red. So it's like, I don't even know how this would work, but it must be possible. So so the color's there. So what's going to happen? Well, okay. Over here, what will happen is that this is R, this is G, and this is, this is B, and this is G, okay? So what will happen is that for that point right there, R, all right, so will be, right, so B, R will be greater than 0, G will be less than 0, and B will be less than 0. G is going to be less than 0 because okay, everything out here along this line is where G is less than 0. So this section here that I'm marking, this whole section here is G less than 0. Okay? And this section here this is b less than 0, right? And this section over here is r less than 0. So here, this is not in this section, so r is greater than 0. But it's definitely in the section of g and b less than 0. So what will come out of the sensor, if the sensor has x, y, z, the sensor is actually designed so that the color matching functions are in x, y, z, say. And then you take the x, y, z and you convert it to RGB. What you'll get, and we'll talk about how to do that in a minute, then the RGB values you get, two of the values will be negative. But the value of the format can only store 0 to 255. So what are you going to do?
0.
Desaturator.
You'll have to do something. So the answer is, well, there's a lot of different things you could do, but as engineers, what are you going to do? You're going to clip them, or you're going to do whatever it takes, okay, to get paid. Because the problem is that if you go back and you tell your employer or the person who's, the person who's paying your salary, and you say, "I'm sorry, it's impossible to do this. I can prove theoretically that it can't be done," and then they'll say you're fired, right? So instead, you have to say, "Yes, sir, I can do it. I'm going to successfully solve your problem," okay? And then you just, you do whatever it takes, okay? The real world is sometimes a dirty place to deal with, and you're going to have to make some approximations. Yeah?
Could we normalize the other pixels according to this one?
Yeah, you could do a lot of things, okay? It's like the Wild West, okay? You're gonna have to do some nasty things. You might try contracting them all in. You might clip them here. Whatever you're gonna do, it ain't gonna be pretty, because you're gonna have to make some approximations. You're gonna have to break the theory, okay? So then the question is, well, which is least damaging? Right? Well, you'll have to. You can study that. You can ask. Well, some things might seem theoretically better, but they may not look as good. And there's been a lot of study of how to do gamut compression to try to give the illusion of having reproduced all the colors while remaining within the constraints of the real device. So, by the way, I should mention that. In the particular case I gave you where the person had the red scree suit on and their head was just flat, okay? Well, what do you think they did? They clipped it, because there's no gradation in color anymore, so they just clipped it off, and you lost all the detail. So it would have been nice if you maybe had been able to retain some of that detail. Maybe it would be less noticeable, less egregious. So, okay. But that's what happens, okay? And so these are out of gamut for the format. So you can be out of gamut for the storage format. So how would you extend the JPEG standard to be able to handle colors that were out of gamut, to have a wider gamut? So if we have some format with RGB, the 709 primaries, and the values of RGB have to all be positive, if you were in charge of the universe and you could change all these standards to make them better, to make the world a better place, okay? What would you do? You'd have to make some compromises, right? There'd be some trade-offs here. What would the possible solutions be?
Store it using more bits.
You could store it using more bits. If I go from 0 to 255 to, say, 16 bits, okay? And then, so 16 bits would be, I don't know whatever that number is, 0 to 2 to the 16th minus 1. Is that going to be any better?
I would think so. You could certainly fit more than the 255 values.
That's true. It would be better in that sense. Would it solve this problem?
Sign bits.
This is a great exam question, by the way. Somebody needs to write this down so I can remember to put it on the exam.
Okay.
Any thoughts?
I think Albert made a good point. He said, what if we sign the bits?
Yeah, you need negative values, right? But the negative values don't have to go all the way, don't have to be as large.
Right.
So using a standard way of signing a digital value is to use what do you call it? Two's complement, right? But that uses up an entire bit, which is quite a bit to use. So, so that would be what would be the disadvantage of using unsigned signed? Then it would be
half your color space would go to negative.
Yeah, so the resolution of the color space would go down. So what would be the practical disadvantage of that you might imagine seeing?
Quantization in the...
You'd see quantization, right? Because what will end up happening is if you make these steps too large, all of a sudden you'll see steps, particularly, where would you typically see those? You'd see them in...
Shadow.
Generally in... I'm looking for a word that starts with the letter S.
Shadow.
Huh?
Shade or shadow.
Yeah, well, another letter S. SM.
Smooth.
Smooth, in smooth regions, right? If you have smooth regions, you'll notice these little fine discontinuities, right? Mm-hmm. And so what'll happen is that so there's if you're going to constrain yourself to 200 to 8 bits per pixel, then there's no perfect solution because you can basically move these points out, okay? But you waste if you move them out, well, you waste your step sizes become larger. If you move them in, well, your step sizes become finer, but your gamut goes down. So there's a sort of a trade-off between gamut and step size. Well, you can add more bits, but that's a little tricky too. There's been various extensions, attempts to extend the standard for Srgb or for color spaces in general to handle larger gamuts. And they've met with varying levels of success. As a practical matter, the simplest formats have continued to be dominant. And then the only other thing that people really practically do in photography, and maybe I'm speaking out of turn because I'm really not a practical expert at some of this, is they use raw formats, which I think becomes reasonably common among photographers. Yeah. Okay, so that gives you an appreciation of the trade-offs. And this is a beautiful engineering problem. Engineering problems involve trade-offs between things. You know, engineers deal with things when the world's not perfect. Okay? Okay, so coming back to the computer, yeah, okay, so we, let's see. Okay, I think we've been through all this. Okay, white point. Now, this is a very tricky issue. So, what is white point? Okay, well, white point is a tricky thing to describe because, well, I mean, I'm gonna start off by giving you a sort of a philosophical definition, and then I'm going to talk about and then I'll talk about it in a more precise sense. Okay, but first of all, white point is a complex concept because it actually the same words refer to more than one technical concept. Okay, so and our treatment of white point is going to be very limited in this class. So. Because we won't be able to get into the more complicated aspects of it, but you know, in my view, one of the most basic applications of white point is just pure calibration. When you define a color space, if we can go back to the paper again, when you define a color space, I'm telling you, if I give you Rgb values, if I tell you the chromaticities of the Rgb values, then when I specify the Rgb values, if you give me the chromaticities of the Rgb primaries and you give me Rgb values, now I mostly know how to interpret those values. So if you give me 3 values of red, green, and blue, okay, you tell me what the primaries associated with those red, green, and blue values are. I can reproduce the color, okay, in the sense of color matching, okay. I can reproduce the color, except for there's one missing number, okay? The one missing number is the white point. And the reason the number is missing is that I don't know the relative mix of red, green, and blue. If I made the red, green, and blue primaries relatively brighter or darker relative to each other, okay, then when I mix the red, green, and blue values together, I'd get a different white point, okay? So what would happen is that it's not enough to know just what wavelength or chromaticity the red, green, and blue primaries have. I also have to know their relative intensity. Okay? And white point is the conventional way for specifying that. So, in other words, white point is just like a specification so that when I'm talking to another person and I give them RGB values, they understand what those RGB values mean in the sense of colorimetric calculation, in the sense of XYZ. They can calculate the underlying XYZ associated with our RGB values. XYZ is can be thought of as a standard interchange space. So one way of thinking of this problem, by the way, this used to be extremely out of vogue, and when it was extremely out of vogue, I still used to say it. So the whole world has finally changed to agree with me, thank goodness. Now they finally saw the light, okay? So what happens is that you can have XYZ and LAB. These are kind of universal standards of color. There's still some issues here, right? Because we had the 10-degree observer and the 2-degree observer, but those are relatively fine points. Most people within a particular context will agree on XYZ being essentially a gold standard for the specification of color, okay? But now you have some sort of color space, like you have RGB. Well, first of all, RGB can be anything. So often what we'll do is we'll say, well, it's sRGB. We're going to talk about that later. sRGB is typically the color space used for encoding like JPEG images on a digital camera, or if you have video. This is widely used for consumer applications, or if it comes to your TV set, it's sRGB generally, okay? But people might have other color spaces too. They might have a device-dependent RGB. So they might have a particular device that physically has colors associated with it. So this would be this might be a display. Or you might have a printer here, which takes RGB. A printer can take RGB input. It means it has to be converted to whatever the native color space is for the actual printers, which is going to be some sort of nonlinear transformation. But this could be a printer. Okay? Okay, so this might be, and over here you might have a camera. This might also be RGB, or this might be some sensor space. I'll call it raw. Okay? So what happens? So one possibility is you could have hundreds of these, because every camera in the market, you can have the HP digital camera and the Canon digital camera, and you could have the Epson printer, and then you could have the Xerox something or other. And so there could be thousands of these, and then what you could do is you could have an endless employment for all the engineers in the world, each calculating the transform for every one of these to every other one, right? Because if you have 1,000 different devices, then you have 1,000 squared over 2, roughly, interchanges. It becomes unmanageable, right? It's like what they call the Tower of Babel. Okay, so what happens is that the standard engineering solution is that we have an interchange space. So what we do is we go to some standard space, and then we convert to the other space. Mm-hmm. So this takes the problem from being order n squared to being order n. So the disadvantage of this is that any deficiency you have in this interchange space is inherited by every device. So if the interchange space is sRGB, which is actually what it often is in consumer devices, you're limited by sRGB. But the nice thing is it makes a simpler, more unified methodology for handling the data. Okay. It used to be that there was a strong belief that we should have basically ways of converting directly between every box, and now I think everybody's finally given up on that, and they just do this kind of interchange. So okay, going back to the slide. Okay, so all of this is basically just calibration. Okay, so that's the most basic meaning of white point. It's the most, in my view, the most fundamental, because if you don't do that, it's really hard to do anything else. Okay. So, but white point has other meanings which are very important. One is color constancy. So early on, when we first started, I talked about I talked about color appearance. And I said how the same spectrum of light can appear to be a completely different color depending upon the context in which you see it. And we saw that optical illusion, which was very strong. Okay? So white point is often used to do that correction. The problem is this. If you take a picture of something in a scene, and then you view the same picture under different lighting conditions. So when I say picture, so let's say you actually produce, you have an emissive display, but you see the same spectrum of light in a different environment. So the illuminant in the room, the surrounding illuminant in the room is different. Your perception of those colors will be different. For instance, when you look at things under fluorescent lamps or under incandescent lamps, the actual spectrum of the light is very different, but your perception of the colors is relatively constant. That's called color constancy, and it's often used to. Okay, so when you reproduce a color in for some application, the problem is that, okay, this gets back to the employment issue, okay, which is that you may produce an image and you say, this image quantitatively is a precise match to the data I have, and by God, I believe this, and I am invariantly going to produce this because I believe in the consumer's right to see exactly what was there. And they're going to say, thank you very much, you're fired, okay? Because the consumer wants to see a picture they like, okay? They don't care if it's a colorimetric match or not. They want it to look good, okay? Okay? So the color imagery that we're studying this course is very important because you can't, you can't run until you can walk, and you can't walk until you can crawl, okay? So you have to understand how to do a colorimetric match, but in the end, nobody may want it, okay? It may not be useful, okay? Because it may not look good, okay? So color constancy deals with that issue. How do you adjust the colors, not just so that it's a colorimetric match, but so it either looks good, or actually so that it appears the same color, because the appearance of the color may be very different than the spectral match, okay? Or so it looks good, okay? We're not going to deal with any of that here because it's way beyond the scope of this class, okay? Here we're just trying to learn to crawl, okay? Now, the other thing, which is the color constancy involves human beings, and maybe it should have been the third point. But a relatively more straightforward but still very complicated issue is gamut mapping. So here, human beings think things are simple because they're good at them. But when you actually go to do them yourself, you find out that they're much more complicated than you thought they were, okay? So, for instance, everybody knows that if you go to a photocopier and you photocopy something, you want the output to come out and look the same as the input, right? Seems very simple, right? Except for it's not. Because guess what? If you put the paper on the copier, is the paper on the copier going to be the same color as the paper that comes out of the copier? No. I'm copying a newspaper. It's a different color. The paper is a different color than the paper in the copier. It's not just a little bit different. It's completely different. It's not the same color at all. I mean, look at a piece of newspaper, right? It's very yellow and it's dark. Or Time magazine, it's going to be a different color than the paper that comes out. So the question is, what does the consumer want? You can produce a colorimetric match, but that may not be desirable. Do you want the actual copier to reproduce the color on the paper that you're copying onto the? And even if it can, it may not be able to, because maybe the paper you're copying has a brighter white than it would have to have white ink to make the paper whiter, right? So it's just not realistic. The problem is the gamut of the actual source data is different than the gamut of colors that are available to the output of the printer, because the printer's gamut is limited by the color of the paper. So gamut mapping is a very important aspect of white point. We will ignore that point also, okay? Because it's also beyond the scope of this course. Perhaps not as far beyond, but also beyond. So we're only going to worry about the issue of white point in respect to its use as a way of defining a translation language when we're talking to each other, that we're talking the same language, okay? Okay, now, so in that context, we only have 25 seconds left. White point, okay, first of all, we're going to have a spectrum of light. Okay, we'll get back to it next time. All right, thanks a lot. Bye.